Right. Very good. Yeah,
Final
thanks.
speaker of the session is Senthil Todadri, who's also a condensed matter theorist and is a professor of physics at MIT. And he's going to tell us about anyons in quantum matter.
Yeah, so it's been wonderful to be here. Love coming to ICTS and the wonderful atmosphere here, meeting old friends, making new friends. And this conference has been particularly stimulating. It's very different from the typical kind of conference I or probably any of you goes to. Lots of talks on lots of different topics, all blended with each other. So it's been great. So wonderful job to the organizers. Abhishek and Rajesh and everyone else in the committee. Uh, so I'm going to continue on the same theme as Philip and Shankar, anyons and quantum Hall. Some of you might wonder, why are we so obsessed with quantum Hall? It's beautiful, right? It's one of the big discoveries, perhaps the biggest discovery in quantum many-body theory in the last 100 years of quantum mechanics. Okay? So I can go very quickly through the introduction because by now you've heard lots of talks. We know that, we heard about Bose's wonderful insight about identical particles in quantum mechanics, and everybody knows that early on, people decided that there were two distinct kinds of particles, bosons and fermions, and they were understood from a modern point of view by thinking of many-body wave functions of identical particles as objects that transform in one-dimensional representation of the permutation group that characterizes the exchange of particles. Okay. Now, it was only much, much later, several decades later, that people realized that rather than focusing on the wave function and asking how it transforms, it's better to focus on amplitudes of distinct topological classes of the many-particle system when you think in the language of Feynman path integrals. Okay, and it was realized starting in 1977, 50 years after the birth of quantum mechanics, that that in two space dimensions you can have anyons. Right? So let me quickly review the argument. It's already been mentioned in Philip's talk. So if you just take two particles in any space dimension, d bigger than or equal to 3, and you think about return paths of the relative vector separating these two particles. So then the relative vector, so long as the particles don't crash into each other, you can take the relative vector to live topologically on the surface of a sphere, and there's this, on the surface of a sphere, an exchange trajectory corresponds to something like this, where you start, say, at the North Pole and come to the South Pole, and then you can have a double exchange thing where it just returns to the North Pole, right? And these are just, these are the only two topologically distinct classes of particle trajectories for this relative coordinate in this two-particle quantum mechanics. So you can assign different phases to these two kinds of trajectories, and the only possibilities of boson and fermion statistics, you either have an exchange phase of +1 or an exchange phase of -1. Now in 2 dimensions, the story is different because the relative vector now lives on a circle, S1, and then you can have an exchange trajectory where the relative vector winds around by pi, or it winds around by 2 pi, or by 3 pi, and so on and so forth. And all of these are topologically distinct, and you can assign different phases to all of these. Right? So that was the basic insight in this paper, and sharpened somewhat by these other papers, and extended. Mathematically, the right way to think about it is that the distinct classes of particle trajectories are described by an object called the braid group in 2 dimensions, which already made an appearance in Philip's talk, as opposed to the permutation group in 3 or higher dimensions. So identical particles in 2D form representations of the braid group, and there are one-dimensional representations where the braiding multiplies the state by a phase. And if the only effect is multiplication by a phase, then if you braid multiple anyons together, right, then the net phase does not depend on the order of the braids, and you get what are called abelian anyons, which again has been mentioned. But then the braid group also has higher dimensional representations. And a crucial property of these higher dimensional representations is that if you have n localized anyons, they have a Hilbert space that grows as grows as d to the power n for some constant d. So there's a huge Hilbert space for these n anyons. And now braiding multiplies the state by a unitary matrix. Each braiding operation corresponds to the action of a particular unitary matrix on the state. And given that it's a unitary matrix, now the order of the braids matters. And so these things are called non-abelian anyons. Right? Both kinds of anyons are possible. And so that's the story. Now, the next big insight in this business came from Bert Halperin initially, and a bit later by Arofa, Schiffer, and Wilczek. That is that anyons can occur as emergent quasiparticles in quantum matter. Right? So in quantum matter, in our universe, maybe not in alternate universes, microscopic degrees of freedom are things, or electrons, or maybe they're bosons if you're in Emmanuel Bloch, right? Or maybe they're spins or things like that, right? And the low energy physics, all kinds of things can happen. And in particular, it may be that the low energy physics, you have a many-body ground state with a gap. And in this state, there will be well-defined quasiparticles. But these quasiparticles may not have Fermi statistics or Bose statistics. They may have anyon statistics. So that was the crucial insight that people had. And so the question then is, where can we find anyons? And as you've heard, and as probably everyone knows, the fractional quantum Hall effect is the best example that we have of a system where we find anyons. And as you also heard from Subhi's talk, maybe people remember, there are certain ground states of quantum magnets called gap spin liquids, which also theoretically we know will support anyon excitations. We don't yet have good experimental, a concrete experimental realization of such a gap spin liquid in a naturally occurring quantum magnet, right? But people are hoping that it will show up soon. And of course, quantum processors of the kind that Pedram talked about, you can just engineer states. You can prepare states that support anyons as defects or something like that. And Pedram showed many examples of such designs. So let me talk about the quantum Hall effect, since that's the one experimental example where we know for sure that we have anyons, right? So I'm going to give a high-level discussion of the quantum Hall effect. You heard from Shankar a beautifully detailed description of what it takes to get the integer quantum Hall effect. So I'm going to assume that all of Shankar's conditions apply, that you do get a quantum Hall effect, and then let's ask what the phenomenon is. So you run a current, you take a 2D material, and you run a current in some direction, and you ask where, what the induced voltage is, right? And the statement is that the electric field locally, if there's a current density in this direction, there's an electric field that's perpendicular to the current. So this current flows without any dissipation because the current is perpendicular to the field with a coefficient that is this Hall conductivity, okay? And in the quantum Hall effect, this Hall conductivity is quantized in units of E squared over H with some times a rational number. P and Q are co-prime integers. If P over Q is an integer, then it's the integer quantum Hall effect. Otherwise, it's the fractional quantum Hall effect, right? And you've seen this case many times by now. There's all these plateaus. So this is the 1/3 plateau, and you get all kinds of other things. Okay, so where can we see the fractional quantum Hall effect? So the classic realization is electrons in a continuum in a strong magnetic field, right? Philip Kim's, the entire talk was based on that system. Now, as Shankar briefly mentioned at the end, there are new realizations. You have electrons on a lattice with broken time reversal. You don't have a magnetic field, but you have broken time reversal, and perhaps the time reversal is even broken spontaneously. And there's a huge literature, at least theoretical literature, suggesting all kinds of ways to engineer cold atoms to coax them into this quantum Hall state. And as far as I understand, that's not yet reached fruition, but people are getting there. There's some demonstration that you can do it with 2 atoms, I think. But it will, yeah. So 2D electrons in a strong magnetic field. The single electron physics is that you form Landau levels. And the entire story of the fractional quantum Hall effect happens when you have Coulomb interactions in partially filled Landau levels, and you have disorder, as Shankar just emphasized in the last talk. And this wonderful microscopic theory, again, going back to the early days of the field, pioneered by Laughlin and various others subsequently. So there's a very mature understanding of the fractional quantum Hall effect in this context. Now, so the question then that I want to talk about next is about this possibility of a fractional quantum Hall effect without an external magnetic field. Now, Shankar mentioned this at the very end, so let me repeat what he said with slightly differently. So if you have a Chern band in a lattice electron system, if you have a band structure, right, and the bands have Chern number, now for those of you who are not solid state physicists, let me tell you how to think about a Chern number. The Brillouin zone in a lattice system, there's a Brillouin zone, and the Brillouin zone is the torus, right? In 2 dimensions, it's a 2 torus. And this 2 torus can enclose a magnetic monopole. And so long as that monopole is strength is not 0, you say that the band has a Chern number. So in other words, there are wave functions, momentum space wave functions defined on this torus. And the Chern class of that, of this collection of wave functions is the Chern number. That's why it's called Chern band, and so on, right? So you might have thought that if you have fractional filling of a Chern band, that you could get a fractional quantum Hall effect. Now, this theoretical possibility and a numerical demonstration in toy models happened in 2011. So Shankar mentioned some of this work, him and several other people. So this phenomenon can happen, right? So the questions that remained after 2011 are, how do you get Chern bands in a real 2-dimensional material, right? How do you break time reversal spontaneously? And how do you get the bands flat enough so that Coulomb interactions can dominate and give you an interesting many-body correlated state? And then there's a final question that one could have asked, and some people did ask this question, why is this interesting? Right? After all, we know the quantum Hall effect can happen in a magnetic field, so what's the big deal with it happening in 0 field? Right? I'll address all of these questions, including the last one with a qualifier. I'll say, I'll answer the question of why is this interesting to me? Hopefully, you'll also find it interesting. Okay, so there's been rapid progress on all of this in the last few years, and so let me give you a flavor for what the progress has been. So since 2018, leading up to now, theory has consistently said that the best place to look for this is in these 2D Moiré materials, which Mandar talked about at length yesterday. So a Moiré material is formed when you take 2 slightly different crystalline structures and interfere them with each other to produce a very long period interference pattern. A periodic but very long period interference pattern. So there's various Moiré graphene systems that early on we and others realized will have all these ingredients that are perfectly suited to finding this fractional quantum Hall effect in 0 field, in graphene systems, and also in these Moiré semiconductors based on things like transition metal dichalcogenides that Mandar also mentioned. So experiments, so there's a lot of theory saying that Moiré is the best place to look for this. And there's big success in the last year and a half. First in twisted transition metal dichalcogenide material, molybdenum ditelluride, and soon afterwards in multi-layer Moiré graphene by various experimentalists. So I presume a large fraction of the audience knows nothing about Moiré. materials. So I'll just give you 2 facts about moire that are useful to know to follow a bit about what's going on. So the 2 facts are this, right? First is that the electrons in these materials live in 2 separate valleys that are related by time reversal symmetry. Okay, and what the theory tells you is that in many of these moire materials, the bands in each valley have Chern number. If in one valley they have a certain Chern number, in the other valley they have the opposite Chern number, right? Because the 2 valleys are related by time reversal. And the second thing is that they are highly tunable. And this is part of the reason for the excitement about moire in the condensed matter community. You can very easily change the ratio of the electron kinetic energy to the Coulomb interaction in a single material using just some voltage, some gate voltages and things like that. Okay, so how do you break time reversal symmetry through interactions in this kind of system and produce a Chern band? So the theory is actually very simple, but the conclusion coming from this is actually very dramatic, right? So let's focus on a situation where you have a moire lattice, there's a periodic lattice. Let's imagine that the electron density is such that you have 1 electron per moire unit cell, okay? And you have, the electron spin is a degree of freedom, at least in the graphene systems. And then independently, there's also the valley degree of freedom, right? Now, suppose the valley and spin, if it's present, that they both order ferromagnetically, so then you break time reversal symmetry, right? Now, I already told you that in many of these systems, in each valley, you have Chern number. So let's say in one valley, you have Chern number C. Then in the other valley, because it's related by time reversal symmetry, you'll have Chern number minus C. Now, if the total filling is 1, you fill one of these 4 bands, right? So with interactions, you will spontaneously polarize the system so that you exactly fill one of these 4 bands, right? If you didn't have interactions, you'll equally occupy a quarter of each of these bands, and you'll get a metal. But if you have strong enough interactions, you can polarize in this flavor space, just occupy one of these 4 bands. And since each of these bands is a Chern number, you'll get a Chern insulator. You'll get a full Chern band, and that'll give you a Hall conductivity, a quantized Hall conductivity, okay? So this sort of ferromagnetism is what enables, that's the precondition for observing this phenomenon of the zero field quantum Hall effects. So this, we and others discussed it theoretically, and shortly thereafter, the experiments showing that this kind of thing indeed happens for the integer quantum Hall effect in many of these systems. And I want to point out, how remarkable this story is. Because, let me just focus on the ferromagnetism for the time being, right? So this is a seemingly very simple mechanism for ferromagnetism, but this ferromagnet is unlike almost any other ferromagnet known to humankind, right? The majority of the magnetization comes from this valley degree of freedom. It turns out, if you work out the numbers, the spin contributes relatively little to the magnetization. If you take iron, cobalt, nickel, most of the magnetism comes from the spin degree of freedom. Here it's coming from orbital motion of the electrons, right? It's what people call an orbital ferromagnet. It's orbital motion that's producing ferromagnetism. And second, if you have a chemistry background and you ask, name an element that can go ferromagnetic, carbon is the last thing that you'll say, right? So from a chemistry point of view, it's spectacular that, that layers of carbon can develop ferromagnetism, right? So, it's spectacular from that point of view. And furthermore, not only is it a ferromagnet, it has a Chern number, right? So it's actually pretty amazing. But, that's not the purpose of this talk. More amazing things are what happens when you have fractional filling of these Chern bands. So in the stress-state MOT2, this is the kind of data that emerged from Choudong Chu and others last year. So this was at a lattice filling of 2/3. This is an illustration. You know that you have ferromagnetism because as you tune a field and you measure the Hall resistivity, you see hysteresis at zero field. Ferromagnets have hysteresis, right? As the direction of the magnetization depends on the direction of the field, and as you cycle back, you go through some hysteresis loop. So depending on which direction you cycle in, you get a loop. But beyond this coercive field, this Rxy is quantized at 3 over 2 h over e squared, which is precisely what you expect for a fractionally quantized quantum Hall system. Okay, and the similar things are seen at filling 3.5 and so on and so forth. The same phenomenon was also seen in a different system. This is multi-layers of graphene stacked in a particular way. In this example, the first one, it turned out you needed 5 layers. We now see this phenomenon also with 4, 5, 6, and even 7 layers. So this had 5 layers of graphene aligned with this boron nitride just on one side. So that produces a Moiré superlattice that affects the electrons that live close to the aligned HBN in this top layer. But the experimentalists also applied an electric field perpendicular to the stack, which is such that it drove the electrons away from where it was aligned with HBN and drove the electrons to this bottom layer, right? So in this setup, there's a phase diagram that the experimentalists can come up with as a function of this perpendicular electric field and the density. Actually, the very fact that they can draw such a phase diagram is spectacular, right? This is the kind of thing that, pre-Moiré is very, very hard to do in condensed matter physics, right? But now it's a routine thing. So this corresponds to lattice filling of 1, and you see this integer quantum Hall effect where Rxy is 1. And here you have an example of a fractional quantum Hall effect where you see an Rxy of 3 over 2 h over e squared. Okay, so given these kinds of observations, so there's some interesting many-body state, right? In general, in quantum many-body physics, there's 2 kinds of questions which are both important to ask, but they are of a different flavor, right? One could call them the what and the why questions. So the what question is, what is the state? Can we understand the universal properties of the state and characterize the state, right? And the why question is, can we justify why the state exists in the first place, given the particular microscopic system, right? So let me start with the what question. So universal phenomena in the fractional quantum Hall effect, or in the usual fractional quantum Hall effect in the Landau levels, it's pretty well understood. You have the precisely quantized Hall conductivity, you have fractionally charged quasiparticles, you have anyon statistics, you have one-way current carrying edges, and so on and so forth. Now, it turns out, and I think you heard Philip give beautiful evidence for this, all of these, I guess Philip didn't talk about this either, all of these have by now been confirmed in Landau level realizations. Some of these, this and these last 2, just in the last few years. The story of the edge state was also really clarified experimentally only a couple of years back. So the story is in good shape for Landau level quantum Hall physics, but theoretically, we want to abstract away from any characteristic of the Landau level, and we want to think about the fractional quantum Hall phenomenon more generally, abstracted away from the setting of Landau levels in which it was first discovered. Okay, so let me run through some general ways to infer properties of the quantum Hall state, given the fractional Hall conductivity. So why the fractional charge, right? So this goes back to ways of thinking that Lofgren initiated early on in the 1980s. Suppose you have an angular shaped sample with some tiny inner hole, and you thread a magnetic flux through this inner hole and slowly increase it from 0 to a flux quantum. Faraday will tell you that there's a circulating electric field, which is given by the rate at which this flux changes. So since the electric field is circulating in the tangential direction and there's a Hall conductivity, there's now an electrical current that flows in radially inwards. And if at the end of this process, as you increase to h over e, you can calculate the net, the time integral of the electric current that is transporting charge inside, and the net current that's pumped from the outer edge to the inner edge is exactly given by the Hall conductivity. And so the Hall conductivity is P over Q. This means that you pumped a fractional charge from the outer edge to the inner edge. So you should think of this process as nucleating a quasi-particle with this fractional charge near the inner hole, right? So this ties the observation of fractional charge to the observation of the fractional Hall conductivity, right? Not without any reference to any other theory. There's a similar argument that you can make for why you need anyons, which makes no reference to the Laughlin wave function or any other microscopic detail. So the idea, once again, is to imagine this flux trading process. But then once you have a full flux quantum, you can undo it through what's called a large gauge transformation. Condensed matter physicists might be familiar with this paper, the very beautiful paper by Sean Young and Byers. Now, the fact that you can undo this means that the threaded flux, whatever effect it has, maybe it's nucleated, it will have nucleated this quasi-particle, this fractionally charged quasi-particle, should not be detectable in the bulk, right? So in particular, if I take some other quasi-particle in the bulk and move it around a loop that encloses this hole, then the fact that it should not be detectable implies that there's a braiding phase when A goes around V, which is precisely e to the 2 pi times Q of A, where Q is the charge of this quasi-particle, right? So this is a very, very general result that doesn't rely on anything microscopic. But if I apply this, if I take A to be V itself, then I see that since V has fractional charge, it implies that V must have fractional statistics, right? So I immediately conclude that I have fractional statistics, that this fractionally charged quasi-particle is necessarily an anyon with intermediate statistics, okay? There's a more sophisticated version of this argument that tells you that V, in fact, is an abelian anyon, okay? So, yeah. So it's amazing. So there's just one measurement that we need, irrespective of the microscopic realization, which is that of the conductivity tensor. Sigma xx is 0 and sigma xy is quantized. This tells us the only way this can happen is if the ground state is topologically ordered. The field theorists describe it by saying that the low energy physics is described by a continuum topological quantum field theory. And for Q bigger than 1, where there's the fraction, we'll conclude that this IR theory must have gap fractionally charged anyon excitations, okay? Now there's further constraints on the IR theory that you can obtain. Given that you have one abelian anyon V with charge P over Q and some fractional statistics, you can combine two of them and produce another anyon, right? And you can keep doing this till you get a completely local object, right? So you can produce a tower of abelian anyons with this statistics and with this charge. And if n is some multiple of Q, it goes back to something which has trivial statistics and trivial braiding with everything else. And for some multiple of Q, you expect that this object is local and does not braid non-trivially with anything, right? Now, the field theorists in modern times have an interesting way of stating this fact that you have this tower of anyons as a symmetry statement. The statement is that this IR TQFT has what's called a generalized symmetry, a one-form symmetry with ZLQ one-form symmetry with a particular structure that's known as an anomaly, right? So this is an interesting point of view that enables you to use various things, about how to think in terms of symmetries and use that to infer properties of the theory. So there's something interesting. There's an interesting question that one can ask, and these are results in a paper that we're about to, that will hopefully finish soon. We've seen that the observation of the fractional quantum Hall effect implies the existence of abelian anyons, right? Fractionally charged abelian anyons. So we can ask the question, what's the theory with the smallest number of anyons that's consistent with this observation of the fractional quantum Hall effect, right? We already know that we must have at least all these quasi-particles with non-trivial statistics. If Q is odd, then these themselves form a consistent TQFT with Q anyons, and that's the minimal thing that's possible. Now, if Q is even, then the minimal theory is necessarily non-abelian, and it includes the charge P over 2Q non-abelian. And we know we can classify all the minimal theories in this case, and it turns out the non-abelian part is what's called an Ising anion theory, and some very close variants of it. Yeah, we can do a lot more, but this is the. So let me make some comments on this minimality story. So this minimal theory makes no reference to microscopics at all, right? It only depends on knowing the fractional Hall conductivity. So it should apply to any realization. Now, yeah, thanks. So far, there are about 100 different fractional quantum Hall states that have been observed in experiments, different values of P over Q. And if you look at them, almost all of them are just described by these minimal TQFTs, right? So you don't need to know anything really. And you just say, okay, minimality is a criterion, Occam's razor, right? Occam's razor would demand that you get the minimal TQFT. And for most of these 100 states, that's what it is. There are exceptions, particularly in higher Landau levels. And an interesting exception is that filling 12 over 5, where the minimal state is what's called a Jane state, it's abelian. But there's some evidence that perhaps it's some interesting non-abelian state with Fibonacci anyons. Okay, so in the remaining time, let me talk about the microscopic understanding of the zero field fractional quantum Hall effect. So I've talked about universal physics so far, but now let's talk about microscopics a little bit. In twisted MOT2, you have partially filled valley polarized Chern bands. You can do numerical calculations on small systems, and they are consistent with, you see a fractional quantum Hall state, and things look reasonably good. Now, multilayer graphene is in a totally different territory, right? Here, the microscopics is not that well understood. Here, the electrons only feel a weak Moiré potential because the electrons have been pushed away from where the Moiré acts. And it turns out that even the integer state is fascinating. It's, as I'll explain in a minute. And a key idea that's needed to understand the integer state is that the very Chern bands that you need to fill to form the integer state arise in some complicated way due to electron-electron interactions. And the fractional state, the understanding is even cruder. So there's clearly a lot to be done. So let me talk about this interaction-induced Chern insulator. So it turns out you need interactions to not just favor polarize, but also to produce a many-body state with an integer quantum Hall effect. If you do the band structure of this system, which we did at some point, it looks, it's a complete mess. This is not going to give you a quantum Hall insulator. Now, if you improve this band structure by including interactions in a Hartree-Fock sense, then you produce a Chern band. This region expands into this. You produce a nearly flat Chern band with Chern number 1, and that will then agree with experiments. So the interpretation, a possible interpretation of what this calculation is revealing, is that the right way to think about what's going on is that what the many-body system is doing is to really form a crystal. So it spontaneously breaks translations, continuous translation symmetry. But then there's a weak Moiré potential, so the translation symmetry is only approximate. But it spontaneously breaks it in such a way that this crystal is itself topological. It's the electron wave functions in this crystal are topological. So this is a state that breaks time reversal spontaneously, breaks continuous translation symmetry, which is an approximate symmetry spontaneously, but develops a quantum Hall effect at the same time, right? So it's a very bizarre object, but perhaps that's what's going on in the experiments. It immediately raises a fascinating theoretical question, which with some relevance to the fractional quantum Hall state that's seen here. Can you similarly get a zero field fractional quantum Hall effect in a continuum system by spontaneously breaking both time reversal and translation symmetry? So it's what's called a fractional quantum anomalous Hall crystal. It's not really known. It's known that it's possible, but it's not really known whether it'll happen in any realistic setting. Though there's toy models, which where there's some evidence that it can happen. Okay, so I have a minute, so let me just talk about some new opportunities. So what's interesting about the zero field realization, right? So there's many things that one can do that one could not do before. First, the first thing that I put down in this list is that you can imagine doping this fractional quantum Hall phase and studying quantum matter where they're made up of anyons, right? Anyonic quantum matter. you can study phase transitions from the fractional quantum Hall phase to conventional phases. You can study that in experiment, and you can certainly study that theoretically. And these are highly non-standard. They're certainly beyond the standard Ginzburg-Landau paradigm. Turns out they're also beyond a paradigm that's developed in the TQFT literature called anion condensation, and so on and so forth. Now, a lot of experimentalists, what they're interested in this system is to combine superconductivity and the fractional quantum Hall effect. Since it occurs in zero field, there's no problem with combining these two, as opposed to the usual realizations. And there are many interesting theoretical predictions for getting non-abelions by combining these two ingredients. Can I just take a minute and finish? Yeah. So let me very quickly talk a little bit about only this first possibility, and because there's some cool physics associated with it. And yeah, so we all know that Mott translators are interesting. Subi talked about this in his talk. You get high TC superconductivity, you get non-Fermi liquid metals, and so on and so forth, right? So now we have a new kind of correlated insulator to play with, which is this fractional quantum Hall insulator, right? So what will happen if you dope the fractional quantum Hall insulator? Here, the story is very different, right? Because the charge carrying excitations are anyons, right? And the anyons have fractional electric charge. And unlike in a Landau level, so in a Landau level, the anyons see the magnetic field and have cyclotron orbits. Here, on the lattice, there is no cyclotron orbit, right? So the anyons have a well-defined dispersion. They move in straight lines, right? So you can ask what happens when you dope this state. Then you'll get charged anyons at a non-zero density, right? And there's various possibilities depending on which anion is doped. There was an old idea that people had, starting with Laughlin, that a finite density fluid of anions will become a superconductor, right? It turns out this old idea it's a wonderful idea, but it needs to be refined. It needs to be improved, and one can do that. And so let me just flash the results. One result. If you take the 2/3 state, that's the prominent state that's seen in experiments, right? Now there's two possibilities for which anion you can dope. There are two different kinds of non-trivial anions, ones with charge 1/3 and the ones with charge 2/3. If you dope the charge 2/3 anion, then if that's the thing that goes into the system, then you get a superconductor, which is, despite its unconventional origins, it's a relatively tame object. It's smoothly connected to a BCS superconductor, right? The only, only wildness of it is that it's a topological superconductor with 4 chiral minor fermions at the edge. On the other hand, if you dope the charge 1/3 anion, you just, for the ground state at least, you just end up with a Fermi liquid metal, which on top of it, it spontaneously breaks lattice translation symmetry and produces some charge modulation, which triples the period. So it's not, so you may get a superconductor, you may get a Fermi liquid, but with some symmetry breaking. So various kinds of possibilities exist. Now, so this is the last thing I want to say. So it's a novel possibility that one can contemplate, which is what happens if you dope a lattice non-abelian quantum Hall state. Now, so far, these states have not been seen in experiment, but there's no reason why they can't be seen. In fact, there's numerical support for this Moore-Reed state at filling 3/2 and twisted MOTE2 very recently. And in this state, the cheapest charge excitation is the charge E/4 non-abelian. So what happens when you dope this non-abelian into the system, right? So this is interesting, right? So now we have a finite density gas, a finite density fluid of non-abelian anions that are interacting with each other. What does this system do, right? I think it's a great question for theoretical physics, right? Even if the experiments are not there yet, right? And so we've taken a pass at this using field theoretic methods, and it turns out the field theories that we have to analyze are the kinds of things that Spenta and his friends have played with in the past. There are matter-Chern-Simons theories where they're with a non-abelian gauge group, but now the matter field is at finite density, right? And you can analyze the system, and it turns out that it's actually pretty amazing what the result is. If you dope the Moore-Reed quantum Hall insulator, you just get a superconductor, a BCS superconductor, but it's this topological BCS superconductor with uh, uh, with one counter-propagating minor fermion. Amazingly enough, now those of you who know something about the Moore-Reed state know that it has pairing of composite fermions, so maybe it's not surprising that you get a superconductor when you dope. Amazingly enough, the same answer you also get when you dope more complicated non-abelian quantum Hall states, known as the Reed-Desai states, which cannot be thought of as pairing of composite fermions. There's more complicated clustering. Despite that, the answer is the same. You still get the same topological superconductor, right? So this is, it's pretty amazing to me that all this extreme wildness disappears once you have a finite density and you get a relatively tame but still very interesting state, right? With that, I should just stop. I'll just put this up.
Yeah. Thank you very much for a very nice talk. We have time for a couple of quick questions. So yeah, maybe I'll start with Rajesh.
Thanks, Senthil. Wonderful. When you said about this one particular example which was not described by a minimal TFT, I was wondering in what sense does it go beyond? So you're describing still the infrared physics of that state, and you're saying that there is something beyond just TFT, which
the minimal number of anyons.
So you have to add more. So in what way does it go beyond the minimality?
Right. So the minimal number of anyons at filling 12/5 is 5, right? You just need 5 anyons, right? And that's an abelian state. It's just this V and powers of V, 1 V up to V to the 4. But then, and that's, now this Reed-Desai state, so this sector of the theory, that these anyons have to be there in the theory. And this sector just describes some abelian anyons, right? Now this non-abelian sector, which in this case is described by SU2 level 3, which is glued to this abelian sector in a particular manner, right? So it's Fibonacci anyons glued with this abelian sector in a particular manner. So there's a U2 Chern-Simons theory, and then there's 2 levels, right? One for the SU2 part and the U1 part. So yeah, so it has more anyons, right? Yeah.
Senthil, very interesting talk. So as I understand, the difference between the fractional quantum anomalous Hall and the fractional quantum Hall is this sort of, in the fractional quantum anomalous Hall, you have this chunkiness of the Berry curvature, which is not there in the fractional quantum Hall. The fact that there is structure in the Berry curvature distribution.
Yeah. Does that play a role?
Yeah. I thought that was the key physics that distinguishes these two systems. I wanted your comment on it.
Yeah, so it turns out, people have analyzed this kind of thing, and it turns out the important question is not so much whether the Berry curvature is homogeneous or not, but the different quantity. What it is, since you know about the quantum metric, you take the trace of the quantum metric and you subtract from it the local Berry curvature in momentum space. And the question is, in the lowest Landau level, that number is 0, right? If that number is, and that number suitably normalized as 1 in the first Landau level and a 2 in the second Landau level and so on. So the closer that number is to 0, even if the Berry curvature varies in K space, the closer that number is to 0, the easier it is to find quantum Hall states, right? So it turns out in MOT2, that number is not very big. And this pentalayer graphene, the story is much more intricate. In the Hartley-Fock band structure, the complication is that the Hartley-Fock band structure depends on what your density is. At mu equals 1 in the Hartley-Fock band structure, this number is roughly a half. It's between the 0th and first Landau levels. But, whether that Hartley-Fock band, how seriously we should be taking it at partial filling is something we don't know. Many of us have been worrying about it, but we don't know.
Yeah. So thank you very much, and looking forward to your papers. So one question that generally asked in specifically non-abelian phase is that you have to go to actually first Landau level. The 0th Landau level does not give you in gallium arsenide.
That's right.
In non-abelian state.
Right.
So if I'm going to a fractional churn insulator,
Mhm.
what decides that factor?
You know, so the statement that you made that in the zeroth Landau level, you don't get the non-abelian states, that's really a statement about what your interaction Hamiltonian is. No, all Landau levels are isomorphic to each other, right? So what really happens is that the Coulomb interaction projected to a single Landau level takes different forms in the different Landau levels, right? So it's a statement about which interaction in a single Landau level stabilizes which state. Now, in these churn bands, the microscopic is already completely different, right? So you just have to do the calculations, right?
So do we know the full class of interactions that are applicable to these models?
No. So what people did in this example that I mentioned, this is at filling 3 halves, and it's in the next churn band, and they just took the Coulomb interaction and projected it, right? I mean, they might have included some level of interband mixing. I'm not sure. This is a right way to think about it. It's more as guidance rather than as definitive microscopic theoretical prediction. Again, as Shankar said, it's very hard to. You can give guidance, but you shouldn't take it more seriously than that.
Senthil, here.
Yeah.
So how do I understand the age structure for the Chern insulator, fractional Chern insulator? Is it similar to like a quantum Hall physics? Because I don't, here there's magnetic length scale is not there. So what is the size of the wave functions? How do I know the separation between the ages and so on and so forth?
Right. So let me give you the 0th order answer to it. Again, the universal aspects of the edge structure are just determined by the bulk, universal physics, the bulk topological quantum field theory, and those will be identical once you identified the, for instance, for this 2/3 state, we think it's the same as in the Landau level with spin polarized electrons, and so it should have the same universal structure. But the questions you're asking, I think, are not about the universal structure, right? Yeah. Then it's going to be very, very detail dependent, right? Yeah. And unless you do microscopic calculations, you won't know, And so I don't know because I haven't done, nor has anyone else done the microscopic calculation.
Thank you.
Okay, so let's thank the speaker again.